Okay, so we're looking at another statics problem, a static equilibrium. In this problem, we have a uniform long beam, 4-meter long beam, with a weight of 1,200 newtons, and it's supported by a cable as shown in the figure. And it's kind of not really shown well here. This is actually the cable going out this way. This is our cable with the tension. We also have a 2,100 Newton dead weight hanging from the top. So that's this out here. So this is just some weight hanging from the top of 2,100 Newtons. And the beam's not accelerating and it's not rotating. So we know the net torque here is 0. It's in equilibrium. We know the net forces are 0 as well. And we would like to find what is this tension in the cable. And this tension in the cable is 25 degrees from the horizontal, and it's also 90 degrees from the beam itself. So I guess one thing that we're missing in this picture is we didn't put in the weight of the beam itself. It's a 4-meter long beam, but it's completely uniform, which means that the center of mass of the beam is located in the middle of it, halfway through it. So that's at 2 meters, and that's at 1,200 newtons. So that's 2 meters here. Now, if we were to look at the forces here, the sum of the forces equals 0, we would have a tension kind of going up and to the left, a weight going down from the beam and the dead weight, which would mean that technically where this is touching the ground, there should be like some force pushing up and to the right, up to give some more upward force to counteract the weights, and something to the right to counteract this tension. I'm not going to care what this force from the ground is right here. Simply put, I'm making that my pivot point, and as soon as that becomes my pivot point, I have gotten rid of that unknown quantity of the force. So I just said, I don't care about it. Its moment arm position here has an R of 0. What we can now do is we can get moment arms for everywhere else. This is the 2 meters, like we said before. The tension itself is sitting at an R of 3, and the dead weight out here has a moment of 4 meters. Now we can think about which way, in which direction all of these forces are causing the beam to rotate. If we take a look at both the weight from the beam itself and the dead weight out here, they're both causing a rotation of the beam down this way, which is clockwise and negative. This tension kind of pulling the beam around is causing a rotation this way, which is counterclockwise and positive. So we could set up a sum of the tensions equals 0. If we do this, we'll also need to keep in mind that tension is RF times the sine of theta. And what that means is for both of our weights pulling down, if we kind of redraw the picture, we'll have our R vector up like this, and this is the horizontal here, with this being 65 degrees. All of these weights, these forces, if we shift them down to the pivot, which we'll do like this, these are the weights for both the 2,100 and the 1,200. These are at 90 degrees here. And what we actually want is the R crossed with F, so we want the whole thing, or 155 degrees. So when we go and set up the sum of our torques here, equaling 0, these two are going to be negative, so it's going to be negative, and then RF sine theta, 2 meters times 1,200 meters, or 1,200 newtons, that's the 2 and 1,200, times the sine of 155, because that's our angle, and then adding a negative because the block, the dead weight block, is also in the negative direction. That is sitting at 4 meters away, and then 2,100 newtons times the sine of 155. You could actually put these in any order. I just decided to do the block next because it's a negative quantity. And then lastly, plus the tension, which is at 3 meters away, of the unknown tension, and we need its sine component as well. Luckily for us though, this tension is perpendicular, as I tilt my head this way, to the beam. And if we redraw that, that means that the R vector is going out like this. This tension is going like that, and they're perpendicular there. So the sine of 90 degrees is going to be 1. So we don't actually have to put it in. We can just leave it here and set that equal to 0. This is the same thing whenever we multiply these together as saying counterclockwise equals clockwise. If we throw some of these numbers together, let's see, 2 times 1200 is 2400 times the sine of 155. This gives me, oops, what is going on? I don't want that. Go away. I want negative 1014 minus, and then 4 times 2100 times the sine of 155 is negative 35. I would just say 50 here, it's close enough, plus 3t equals 0. Take these numbers, add them to the other side. So that we'll get, let's see, 3550 plus 1014. We're going to get 4564 equals 3t. Divide each side by 3. And we find that t equals just a little bit more than 1500, about 1521, and that's a force, so it better be in newtons. So that's a quick way of kind of running through that problem. It's just a force, torque, static problem. We kind of drew our picture here, kind of doodled on it. We recognized that we didn't actually need the force down here because we turned that into our pivot, which was a smart, clever move. So we could ignore the forces there. We knew the distances, the moment arms to all the different points. We knew all of the angles, which we were able to find with a little bit of geometry, and that this angle was 90 degrees for the tension. And setting that up, from that point it was just algebra. So not a difficult problem, just took a little bit of picturing and kind of working out the math. So with that, it's finished. Take it easy, hope that helped. Hope between this and the previous one you've got a pretty good idea of how statics works. Works like that for everything, so take it easy.